Hello students, welcome back to yet another session. In this unit number 5. So now we will see the apparatus selection and fresh air load. So in this topic, I have divided this into two subsessions, and in first subsession we will see the apparatus selection and then fresh air load, and then we will move on to the next part of this topic. So this is the content of unit number 5. So in next session, in next subsession, we are going to see human comfort and IAQ principles. So here, after calculating the dehumidified air quantity, the air conditioning apparatus may be selected from the manufacturer's performance tables and charts. The necessary data required for this selection are the following, and the required data for the selection are the grand total heat, dehumidified air quantity, apparatus dew point. So this will determine the size of the apparatus and the refrigerant temperature. The performance data also give the bypass factor for the apparatus. So if the BPF, that is bypass factor of the selected apparatus, is not the same as the originally assumed BPF, the portion of the load estimation from form involving BPF is to be adjusted accordingly. So this is very important sentence here. If the BPF of the selected apparatus is not the same as the originally assumed BPF bypass factor, the portion of the load estimated form involving BPF is to be adjusted accordingly. So once the apparatus has been selected from ESHF, that is effective sensible heat factor, that is ADP, that is apparatus dew point, and BPF bypass factor, and grand total heat, the entering the and leaving air conditions are easily determined. So here by selecting this, from this, once apparatus is selected from these points, then it will be easily, the air conditions will be easily determined. So then types of cooling and dehumidifying apparatus. There are two types of cooling and dehumidifying apparatus. One is coil equipment and air washer or spray equipment. So these are the two types of apparatus. And normally, a coil consists of series of tubes through which brine, so that is chilled water or expanded refrigerant flows, and air is drawn over the tubes by a fan. The coil may also be in the form of rows of tubes in a number of circuits. So figure, I will show you a figure here, that is a configuration of 4-row coil, and 7 lengths of tubes shows a 4-row coil with 7 rows of tubes in series in just one circuit. So this is the simple circuit here, tubes in rows and tubes in series. So tubes are placed in series, and air in and air out. So this is a coil type apparatus. As the air passes over the coil, it is cooled and dehumidified or heated depending on the temperature of the fluid inside. The medium inside the coil is correspondingly required to be heated or cooled external to the apparatus. The amount of the coil surface not only affects the heat transfer but also bypass factor. So the bypass factor also depends on the number of rows. The larger number of rows, the closer is the leaving air temperature to the cooling medium temperature. So that is another significant factor here. So table typical bypass factors for finned coils. So here this is rows, deep or depth of coils, and 3 fins per centimeter, air velocity in meters per minute. So meters per minute, and here this is the bypass factor. So that is point for 90, 120, and 150, 180. So we have these are the factors. bypass factors, and for 6 fins and double the fins, so here it is 3 fins only, and now it is 6 fins per centimeter, and air velocity in meters per minute. So that is air velocity meters per minute, that is 90, 120, 150 and 180. For this bypass factor is like this, and these are the values for 6 fins per centimeter. So now the importance of bypass factor lies in the fact that the outside air which gets bypassed so becomes a part of the room load. So now the bypass room air does not affect the load situation. So that is the one note you can remember here. The importance of bypass factor lies in the fact that the outside air which gets bypassed because a part of the room load. So now it is normally part of the room load. So the bypassed room air does not affect the load situation. And air washers with chilled water sprays behave in much the same way as cooling coils, having an effective surface temperature equal to the required apparatus dew point. And the relationship between BPF and ADP and the considerations involved may be summarized as here. And the smaller bypass factor, higher ADP, and a higher refrigerant or brine or chilled water temperature needed, and consequently a smaller refrigerating machine with a high coefficient of performance is needed, and more heat transfer surface since more rows are necessary for smaller BPF. So and also the ADP will be higher and larger coil is therefore required. So larger bypass factor, a lower ADP and lower refrigerant or brine or chilled water temperature is required here, and consequently a larger refrigerating machine with lower coefficient of performance is required. So second point here is less heat transfer surface since less rows are necessary for a larger BPF, and also since the ADP is lower. So factors are 1 and 2 now represent the operating and the first cost respectively and are contradictory to each other. So now both are contradictory to each other, the first point and second point, and it is necessary to optimize from total cost as a guide values of coil bypass factors from the table for typical applications may be used, and this is the table, and coil BPF type of application and example, and zero point 0.2 to 0.5 it is small total load, it is normally residence, small commercial retails, and zero point 0.1 to 0.3 it is typical comfort applications, residences, store, bank, office, and zero point 0.05 to zero point 0.1 higher latent loads are typical indoor outdoor mix, and that is restaurants, canteens. 0 to zero point 0.1 all outdoor apparatus air applications, hospitals, operation room, and other places. So now table bypass factors for finned coil for various applications. So this is the table for bypass factor for of finned coils for various applications. Thus, the apparatus size, coil configuration, and bypass factors are interrelated. All these three are very much interrelated and which are dependent also. Apparatus dew point depends on coil efficiency, surface area, BPF, and lower BPF bypass factor ensures better dehumidification but demands higher first cost. So initial cost is very higher, and proper selection based on application type, required ADP, and manufacturer data ensures optimal HVAC system performance. So next topic in this sub session is fresh air load. So fresh air load is the thermal load introduced into an air conditioned space due to the injection of outside air. It is also known as ventilation air to maintain indoor air quality, dilute indoor pollutants, replace exhausted air or infiltration losses. It contributes to both sensible heat load due to temperature difference, latent heat load due to moisture content. So why this fresh air is required? To ensure adequate oxygen levels, to remove odors, CO2 and contaminants. As per standards ASHRAE and NBC, minimum fresh air is required per person is that is the table. Outside air required per person for different applications. And fresh air components, so Ma, mass flow rate of outside air, and H1 enthalpy of outside air, H2 is enthalpy of inside conditioned air, and then Q fresh equal to Ma into H1 minus H2, where Q fresh is the total heat load added by fresh air. This indicates both sensible and latent heat. If separated, then sensible load equal to Qs equal to Ma into Cp into T out minus Tn. So latent load is equal to QL equal to Ma into HFG plus into W out minus W in. So practical fresh air load calculation steps here. So determine ventilation requirement from standards are occupancy based data. So example 0.3 to 0.9 meters per meter cube per minute per person, and convert to mass flow rate. So Ma equal to V by Vs. So V equal to volume flow rate meter cube per minute, specific volume of outside air meter cube per kg. So then get enthalpy values from psychrometric chart. H1 is outside air, H2 is room air. So apply total load formula Q fresh equal to Ma into H1 minus H2. So we'll see one example. And outside air conditions, TdB equal to 40 degrees Celsius, TWB equal to 27 degrees Celsius. Room conditions are TDB equal to, that is 22 degrees Celsius, relative humidity equal to 60%. So fresh air supply V equal to 20 meter cube per minute. So from chart, H1 equal to 85 kilojoules per kg, H2 equal to 47.5 kilojoules per kg, Vs equal to 0.911 meter cube per kg. So then Ma equal to 20 by 0.911, so that is equal to 21.95. So Q fresh equal to 13.75 kilowatts. So key considerations in design. So cooling coil must be sized to handle both return air as well as fresh air load, and fresh air should be pre-cooled or mixed with return air before reaching the cooling coil. And in humid climates, latent load dominates, so fresh air may be conditioned via dedicated outdoor air systems, so that is thus DOAS, and heat recovery ventilators HRVs. So this is the summary of this topic, fresh air load. And parameter load type is normally sensible and latent input data, that is outdoor air temperature, humidity, flow rate. And design implication, coil size, fan power, duct size. And source of fresh air is AHUs, intake and DAS and HRVs. That's what we have seen in last slide. So there ends this topic, students, and we will see the next subsession in this topic. So textbooks, you can refer any of these books. You can refer the Kurmi book, or you can refer CP Arora or Rajput. So any of these books will give you this information, and you can refer these online materials. And we have more online materials also. You can refer those materials. And so now we will stop here. We will start the next subsession of this fourth topic in next session. Thank you, students.